Hi, dear students. A warm good morning. Let's continue with the chemical bonds and biomolecules, the part 4. The next type of non-covalent interaction that happens between the molecules are the hydrophobic interactions. Now, the term hydrophobe is quite familiar to all of you. It is what? It's a water disliking or just the opposite of water loving. So there are certain particles which are considered to be as water hating or water disliking. Now, what do you mean by this? It just indicates that they are being found to be what? They are low water soluble particles. So when such molecules come in close proximity, they have some interactions, and they are called the hydrophobic interactions. So the relationship between water and certain hydrophobes, that is a one which come into play in the hydrophobic interactions. What do you mean by hydrophobes? They are non-polar molecules, and usually they have long chain of carbons and they do not interact with the water molecules. Now the best example which we have is fat. You know, when fat is being put into water, fat forms droplets as such, and it does not easily mix into it. You can see as dropules, the hydrophobic fat remains undissolved within the water. So when a hydrophobe is being present, now consider this orange color one, consider to be that as a hydrophobe. Uh, Surrounding the hydrophobe, the water molecules would be present. But the hydrophobe and the water is not interacting with each other. And if another hydrophobe also comes into close proximity, what happens? The hydrophobe and the hydrophobe are being drowned together. They are being driven together in the water, and that's the water. So what happens? The water bonds or the hydrogen bonds of these water molecules, which are being found in close in between that will get broken, and the hydrophobic particles become close to each other because they have a high affinity for each other. Okay, and because they are having a high affinity for each other, hydrophobic particles come close to each other, and for them to come close to each other, the water bonds between them will be broken down and the hydrophobe comes close to each other. So that is what is called a case of hydrophobic interaction. So when a hydrophobe is dropped in an aqueous medium, the hydrogen bonds between the water molecules will be broken to make room for the hydrophobe. And see, this is the case what is happening around a hydrophobe. So when two hydrophobes comes into each other, the hydrogen bonds between these two, the water, see, around these hydrophobe there is a water, and around that there are hydrogen bonds also. The hydrogen bonds within the water is being broken, and the hydrophobe will the water molecule does not interact with the hydrophobe, and this is considered to be as an endothermic reaction. And when bonds are broken, the heat is put into the system. And so the water molecule that are being distorted by the presence of hydrophobe will make a new hydrogen bond and form an ice-like cage called the clathrate cage around the hydrophobe. So around the hydrophobe, usually there are hydrogen bonds between the water molecules. And when so that's what this is the cage which has been depicted. And when two hydrophobes come to in happen to interact with each other, the hydrogen bonds between these two will be broken out, and then they will form hydrophobic interactions. So I hope saying that's clear to you. So what are these hydrophobes? As I mentioned earlier, these are regions which do not have a much solubility within the water, or which are being found to be considered to be as water hating substances. Now consider hydrophobic bonds in biomolecules. Hydrophobic bonds in proteins, they mainly arise due to the consequence of the interaction between the hydrophobic amino acids with the polar solvent water. There are certain amino acids which are being found to be water disliking. Now, for example, you have glycine, alanine, valine, leucine, isoleucine, methionine, proline, phenylalanine, and tryptophan. So, all these hydrophobic amino acids are being found to be water disliking. So, the proteins which have these amino acids will be hydrophobic in nature, or the regions where these amino acids have been present will be hydrophobic in nature. I'm not saying that an entire protein is made up of hydrophobic amino acid, but some regions of the protein might be containing hydrophobic amino acids. At that regions, what happens? They will happen to show some hydrophobic interactions. Now, let's have a look on how the hydrophobic interaction, the presence of hydrophobic interaction will influence a particular protein. Now, for the folding of the protein, the hydrophobic interactions do play an important role. And it helps to keep the protein stable and biologically active, because it mainly allows a protein to decrease in surface area, and to reduce the undesirable interactions with water. Besides from proteins, there are many other biological substances that rely on the hydrophobic interactions for its survival and functions. Like you have the phospholipid bilayer membranes, they also have the hydrophobic interaction. So, if these are the regions where the hydrophobic regions have been present um, in aqueous solution, because of the when they have been put in aqueous solution, the hydrophobic regions will get what they will reduce in area and they will remain same. So that is a case at which the hydrophobic interactions help to play in the what to maintain the stability as well as the activity of a particular protein. So not only in the proteins, in lipids also you can see such what hydrophobic interactions. Now let me just if you go to consider the hydrophobic interaction, they are relatively stronger than other weak molecular forces such as the van der Waals forces or the hydrogen bonds, as which we had mentioned earlier. So hydrophobic interactions, they mainly generate by the interactions happening between the regions of the biomolecules where hydrophobic components are being present. It could be what hydrophobic means water hating, or just the opposite of water liking. They will have an interaction with each other. Now, we'll just move on to a case where all these non-covalent forces are being present. Now, consider the case of an antigen antibody reaction. In antigen antibody reaction, we know that each antigen has been found to be specific to that of the to a antibody. So if you consider this key as to be as an antibody, and if this is considered to be as a antigen, the antigen antibody reaction has a lock and key mechanism, and it has been found to be what reversible in nature. That is, sometimes you can find the antigen and the antibody reacting, and sometimes it can be reversed also. And thing that you have to note is that all the forces which act in between an antigen antibody reaction is a non-covalent type of bonding. If it is a covalent bond, it would have been very difficult to make it reversible. So, antigen antibody interaction shows reactions which are similar to an enzyme substrate interaction, because a lock and key fashion is there, and it does not lead to irreversible chemical alterations in either the antigen or the antibody, and it all involves non-covalent interaction, and these interactions mainly happen between the antigenic determinant or the epitope and the what variable region of the antibody molecule. In the antibody, at the tip of the antibody, there is a region where the amino acids are and all that. You should remember, antibodies are being found to be proteinaceous in nature. The amino acids will be highly varied. That is called the variable region or the paratop region. So the interaction mainly happens between the uh, antigenic determinant or the epitope region of the antigen and the epitope region of the antibody molecule. And sometimes multiple bonding between the antigen and the antibody ensures that the antigen will be bound tightly to the antibody. So when a foreign antigen happens to come into your body produces antibodies specific to that of that particular antigen, and they have an interaction with each other. And the main purpose is what? Once the antigen antibody interactions happen within your body will try to nullify the presence of the antigen by either killing it, processing it, or whatever it is. That all happens. And we are talking about the antigen antibody reactions in with a at a case of what? At the level of chemical bonding. Now, when you have an antigen and an antibody, I told you covalent bonds do not happen. It is the presence of non-covalent bonds, okay, non-covalent interactions that play an important role in what antigen antibody reactions. Now, what are the different type of antigen antibody reactions? Can be what non-covalent bonds which can happen between antigens and antibody. Now, take a first case. There would be sometimes moieties on the antigen which are having OH residues, and sometimes on the antibody there would be also certain other molecules which are having oxygen. So what happens in this is a case of hydrogen bond formation. When a hydrogen atom is being it is being attracted towards the electronegative, so a hydrogen bond can come. Or sometimes you can also have a attraction between the positive and the negative units of the antigen and the antibody. In such cases, it is referred to as a ionic bond interaction. Or there would be hydrophobic moieties of the antigen, and there would also be certain other hydrophobic moieties of the antibody. So hydrophobic interactions can happen. Or in other cases, van der Waals interactions can happen. That is, within the atoms or within the moieties of the antigen and the antibody, hydrophobic interactions can come, or when they come in close proximity because of the development of dipole, you can also have van der Waals force of interactions. So all these non-covalent forces which we mentioned earlier, like hydrogen bonds, ionic bonds, hydrophobic interactions, van der Waals force interactions, they all can happen to come into play in the antigen antibody reaction. And the specificity of all these antigen antibody interactions which happen is a cumulated effect of all these non-covalent bonds which we learned across right now. Now, I'm going to another example. This is a protein-protein interaction. Now, you can see this is a hydrogen bond interaction. Then, sometimes if they have charge differences, this is an electrostatic interaction. And here also you have a hydrogen bond interaction. Then, these are hydrophobic regions. Hydrophobic interactions happen between the hydrophobic regions, and here again we have a electrostatic or a ionic bond interaction, and finally again you can see a hydrogen bond interaction. So the non-covalent bonds do play an important role in the stability and the function of various biomolecules, and at various stages of the physiological conditions, different bonds interact, and I hope you got an idea of it. With this, we come to an end of the non-covalent bonds and their role in biomolecules. Thank you.